So we're going to write down the electron configuration of the elements that we can find in the periodic table using our chart here of the correct order of the electron configuration. So right now we're going to do hydrogen and helium, the first two elements in the periodic table. So the first thing is locate the element first. So number one is hydrogen. Hydrogen is here. And we're going to write down the symbol of hydrogen to make it shorter. So hydrogen symbol is H. And then you look at its atomic number. Because it's the first element, so its atomic number is 1. We're going to write it at the bottom left side of the element. That's the representation of atomic number. And we know that the atomic number is equal to the number of protons. And also, if our atom is neutral, whatever is the atomic number, that is also equal to your number of electrons because it's neutral. So if we have 1 as its atomic number for hydrogen, that means hydrogen also has 1 electron. So our task is to write the electron distribution of that single electron of hydrogen. So this is how easy it is. All you need to do is look at hydrogen, look at the box for its label, and it says 1s. So therefore, all you need to do is write down 1s. What does this mean? It means that the electron of hydrogen is in the first energy level and it's in the s sublevel. So first floor inside your s sublevel. That's what it means. So that's why the label here in the periodic table is 1s. After writing down the label of that element here, what we need to do now is write an exponent. The exponent will represent the number of electron. And because hydrogen has only 1 electron, therefore we put an exponent of 1 here on top of s. So we're going to read it as 1s1. The 1 on top represents the actual number of electron for the element hydrogen. So you read that as 1s1. 1s1 is the final electron configuration of your hydrogen because it only has 1 electron. When we proceed to the second element, helium, and we check our periodic table first, check where helium is, and check its atomic number, which is usually the number on top. So helium is represented by He or symbolizes He, and the atomic number is 2, being the second element. So that means helium has 2 electrons. So when we write the electron configuration of helium, it should represent the 2 electrons. So how do we write that down? We put equal sign there. So look at the label of helium. It's still a 1s, correct? So all you need to do is put 1s there. Copy it. Make sure that when you write the s, it doesn't look like a 5. It should look like a letter s. So 1s. Next, what should be our exponent? Because helium has 2 electrons, therefore the exponent will now be A2. So 1s2. And that is the short, direct electron configuration. So we have lithium this time. Li is here in the periodic table, and it has an atomic number of 3 on top. So let's write that down. Li having an atomic number of 3. So that means you should account for 3 electrons. So we should all see 3 electrons in our electron configuration. That's why we always look at the atomic number. So how do we write that down? First, notice the label of Li. It means 2s. Okay? 2s. But that 2s represents already level 2 or energy level 2 and in the s. And we've learned in the concepts about electron configuration, the concept about Aufbau principle, that the electrons should occupy the lowest energy level first. before it goes to the other energy level. And because 2s is already the second energy level, we can't go here right away, but instead, we have to pass by the first floor all the time. Even if the element is not there, we have to begin at the very first energy level. And the very first energy level is represented by 1s. Both of these, 1s. So I'm going to write down my 1s first, representing that the first electrons, the first 2 electrons, will be here in the first floor first. Why will it be 2 electrons? Just count how many elements you pass by in the 1s. I pass by hydrogen and helium in the 1s. That's 2 elements. So I put 1s, then exponent 2. After 1s2, I am done with my first floor. Then I proceed to my second floor, and that's where my lithium is. And the label is a 2s. So I put 2s here. And what should be my exponent? 2s, and it's the first element in the 2s. 2s, this is the only 2s here. I only have lithium as my first. So because it's the first element in the 2s, that will be a 2s1 there. Thereby, if you look at the final electron configuration of lithium here, your exponents 2 and 1 put together, that will be equal to 3. So it means that your 3 electrons of lithium are distributed this way. 2 are in the 1s, and 1 electron is in the 2s. And that's the essence of electron configuration. You distribute the number of electrons of that element in the correct order of increasing energy level. And in the final answer, you must be able to get the actual number of electrons of that element by checking your exponent. I will proceed to beryllium to make this more clear. When we proceed to beryllium, the neighbor of lithium, it is still in the 2s. However, it's the second 2s element. It's the second. So if I will write Be with 4 electrons, it will still be the same, that it will pass by the first floor, which is always 1s2, because there are only 2 elements there, to be followed by 2s, but this time the exponent will now be a2, because it's the second 2s in the periodic table. And when I add the exponents 2 plus 2, that will be equal to 4. It means that I have accounted and distributed all the 4 electrons of beryllium. So let me box the final answer. Let's go to boron this time. Boron. So boron is here. Look at where my red pen is pointing. Boron is here. It has an atomic number of 5. So that means that's a B with atomic number of 5. I have to account for all the 5 electrons. So boron is in the 2p label, 2p. However, we know from Aufbau principle that we cannot skip. And so we have to begin from the first floor all the way to where your element is here. So what's our first floor? The first floor is always the 1s2 for the 2 elements. So I'm going to write that down first. 1s2. So that's my first energy level. Then after 1s2, do not go here right away. You look at here from the left first. So before this green part here, there's still a 2s. So don't ever forget to look at the left side first. So this is your 2s here. 2s, and how many elements are here? There are 2. So that means that's going to be a 2s, and there are 2 elements that I pass by. So 2s2. finally, I'm going to go to the right and reach boron. What's the label of my boron? It's a 2p. So I'm going to write down 2p. But what's my exponent? All you need to do is figure out what portion of the p is boron. Is it the first, the second, the third, or the sixth? All you need to do is count. Boron is in the first box of the 2p, first box. So that means it's the first element of the p. So 2p, 1. And when I check if this is correct, I have 2 plus 2 plus 1. That's a total of 5 electrons distributed. I get the 5, which is its atomic number. So that means my electron configuration of boron is correct. When I proceed to the neighbor, after boron, it's carbon. So carbon will be having an atomic number of 6. So when I have that, I will still do the same. I go to the first floor. First floor is always 1s2. And after 1s2, to the left of the second floor, it's a 2s. So that's going to be 2s, and 2 elements here, 2s2. After that, I go to where carbon is. It's a 2p. But it's the second element of the 2p. So that's going to be a 2p2. And when I add all my exponents, 2 plus 2 plus 2, that's a total of 6. I get 6 as its atomic number. So that means my electron configuration is correct. Proceed to oxygen and neon. So oxygen is 8 and neon is 10. So oxygen is 8 and neon is 10. So we're gonna distribute all their electrons. Let's start with oxygen. So oxygen has 8 electrons and it's a 2p. And you know that you don't go right away to 2p. You have to pass by the first floor. Always the first energy level. And how do you write the first energy level? It's always the 1s, and then the exponent will be the 2 to represent your 2 elements there. After that, second floor, to the left side first, it's a 2s. So that's going to be a 2s, 2 elements, lithium and barium. So 2s2. 2s2. Next, finally, we reach oxygen. It's a 2p. So you write 2p. But what is my exponent? All you need to do is count in what order is it in the p. In what particular number of elements is it in the 2p. So this is my first, second, third, and then fourth. So oxygen is a 2p, 4. Because it's in the fourth, it's the fourth element in the 2p. 2p only. You do not count the s anymore because it's just the 2p here. So 2p, 4. Similarly, if we're looking at neon, which is in atomic number 10, it's still a 2p, but let's figure out what it is. But before we write 2p, we have to go from the first energy level again. So we write 1s2, 1s2, then second energy level, 2s2 first, then 2p, 2p. If you count, what element number is it? 1, 2, 3, 4, 5, 6. So it's the 6th element in the 2p block of the periodic table. So if you check, that is 2 plus 2 plus 6, we have 10 electrons all in all. That is equivalent to our atomic number of neon. So if you've noticed, the full P is a 6. The full S is a 2. Full means you've completed it. And it coincides with our discussion last Wednesday, about the maximum number of electrons. If you look at this before, the maximum number of electrons for the S is a 2 because it has only one room, one orbital. For the P, there were 3 rooms, so therefore the maximum number of electrons is a 6. So that's why in the periodic table, there are also 6 being the maximum for all the P. It's all 6, except this. And for the S, it's only 2 columns. Why 2 columns? Because the maximum for the S is just 2 for the 1 orbital. And if you guess it, for the D block, the maximum of the D block is a 10. So if you look at the middle part, which we haven't reached yet, I'm sorry, the D block is here in the middle. And if you count the number of columns here, that's actually 10 to represent your 10 maximum number of electrons in the D. And similarly, the F block here at the bottom, that has 14 columns, representing the 14 maximum number of electrons for the F sublevel. And that's what we tackled up in the chart last week here. So this maximum number of electrons are your number of columns in your periodic table chart. So that's why it's all right to just count so you'll know the actual exponent of that particular element. So if I'm gonna expand my electron configuration to bigger elements, this is going to get challenging, okay? I'm going to switch to bigger elements. What if I'm going to go to aluminum, which has 13? So let me write down aluminum, example number 9. So the very first thing you need to do is find out the symbol of the element. Your chart only has symbols, no names. So if you're not familiar with the names and the symbols, make sure that you refer to your periodic table with the names. So I have aluminum. The symbol of aluminum is Al. So I look for it here. I found it. So that's Al. And it has an atomic number of 13. So I put the atomic number. The label is a 3p. So that means this is going far already. But I cannot skip all the way to 3p and just shorten it. I have to begin from the first floor, all the way left and right, until I reach my Al. So all the way. So we begin always with the first floor. First floor is a 1s2. So I write 1s2. Done with first floor. Second floor begins with 2s, and there are 2 elements. So 2s2. After 2s2, that will be 2p6. All the full here because I'm not yet done. So you have to maximize it. So all the 6 elements I have to pass by. So that's going to be a 2p6. After that, I'm done with the second floor. I'll go now to the third floor. My third floor starts with 3s. So 3s. And I will pass by 2 elements here. So that will be 3s2. And finally, I reach my aluminum, which is a 3p. So that's going to be a 3p. And first element in the 3p, so that's going to be 3p1. And this is the lengthy electron configuration of aluminum. As the element's atomic number increases, your electron configuration will also become so many to write, because you have to accommodate more electrons this time. Vanadium is symbolized as V with an atomic number of 23. So let's write that down. V with an atomic number of 23. So V is in the 3D already. It's in the 3D. So that means before I reach 3D, I have to move back all the way to the first floor and then make it in order all the way to 3D. So what should be the correct order now? Look at your periodic table. First energy level all the time. So the first energy level is 1s2. 1s2 for the two elements. After that, it's a 2s. Second floor, it's a 2s2. Next is 2p. All the way here, it's a 2p6. After 2p6, we go to third floor, 3s. And 3s has two elements, so 3s2. 3s2. Next is the 3p here. And we maximize it all the way to the end. 3p6. Because we were not done with the elements, so you have to make it full. After 3p6, we go down now to the fourth energy level. And it begins with 4s. And there are two elements here. So that's going to be a 4s2 here. And then finally, after 4s, I reach my v. And my v is a 3d. So that's 3d. And then I'll count in what element number is it in the d. So it starts with this, 1, 2, and then finally 3. So the exponent of 3d is a 3. So the whole thing here, the whole thing that we wrote, is the electron configuration of your